So it's good to have you along. He's got an immense publication record, over 350. He's got a image to rival lose. In the 70s. Disappointed. Yeah, and so, so he'll be talking about his passion about wealth movement, volcanism, but he's also the director of something known as the Faraday Institute of Science and Religion, so he's also come up and giving some talks on that topic, and here a colleague of his, Reverend Dr. Roger Abbott, is along, and he's the one person in the audience, I think, who's not a geologist. So, over to you. Well,
great, thanks. So shall we switch the lights off, and then you can have a little quiet snooze if you want then. Great, thank you so much. I want to talk about work I've been doing in Iceland recently, though I'll start with some older work which is relevant to South Africa, and you'll see why in a minute. And it's work which I've done with a whole team of graduate students, most of them listed there. You can see how many there are. We recorded data for a 2-week eruption, and it took 6 PhDs to get full benefit from it. It was such a rich data set. So that's what I want to talk about, melt movement through the Icelandic crust. This is the eruption I'm talking about, which is Holleran in 2014, a very spectacular fissure eruption. So I want to start off just showing you where Iceland is. You know, it's the other side of the world, isn't it? And it's on a mid-ocean ridge. And the first thing I would just want to talk about is, why is Iceland there? I spent my early career looking at mid-ocean ridges, and then I got fed up with being at sea so much, so I thought I'd look at ridges on land, and of course it is on land across Iceland. And the reason is because there's a mantle plume underneath. So I'll this is your dodgy lead, yeah. If it persists in being dodgy, I might ask if anybody's got an HDMI lead which isn't dodgy. Does anybody have a... There we go. Yeah, this is Ray's dodgy lead. So it's a very dodgy lead, isn't it? Almost any computer will probably have an HDMI going from the display to the computer. I didn't touch it at all, and it did it. Okay. This is just to remind you why you get a lot of melt if there's a mantle plume underneath. And I'm not going to touch anything. So this is the normal. So this has worked from 30 years ago now. No, 99, 2000. Yeah, 30 years. But it's still true today, funnily enough. Here's the lithosphere above the mantle, and that's the geotherm, and that's the solidus. So normally, as you know, the mantle is solid and everything is fine. When you rift quickly, as you do at a mid-ocean ridge, then you move this material up without cooling, so it goes up an adiabat, so that's why it's slightly inclined. It crosses the solidus at a fairly shallow level, and then it melts from then on, and that's the melt that comes out, forms the oceanic crust. And the fact that the oceanic crust is very consistent thickness everywhere of 7 kilometres tells you that the mantle temperature is very consistent everywhere normally. But what happens if you put a mantle plume underneath it? Well, you raise the temperature by not very much, 100, 150 degrees, but because this is fairly close to the solidus, you cross much deeper, and so you generate, for 150 degrees, you generate 20 kilometres of melt instead. So that's why you get so much melt, and that's how you get flood basalts, by rifting lithosphere, continental lithosphere above a mantle plume. So that's really the basis of the work I was doing a little while ago. And this is a little cartoon of what then happens. So here's the crust on the mantle with the mobile mantle underneath it. So if you put a mantle plume underneath it that's 140 degrees C hotter than normal, oh, thank you, I'll hold that, and if this one doesn't do anything naughty,
long enough.
yes, yeah, if that doesn't do anything naughty, I'll leave it, and if it does, I'll swap it. Thank you so much. So you put something hot underneath it, and that's a typical anomaly. It's not very much, 140 degrees out of, well, this is degrees C, it's not even absolute, so it's a very small amount. Of course, that causes buoyant uplift because it's less dense. So typically you're uplifted close to or just above sea level. And that's why at the bottom of flood basalts you often find lacustrine deposits, or terrestrial deposits even, because the area's been uplifted. And then if you rift there, then of course you allow some melt to start to form as it decompresses. As you rift more, it decompresses more, and you get yet more uplift. So it's kind of curious that above a rift, which normally is the deepest part, in the case of a flood basalt, it's the shallowest part. So then the melt can flow downhill on either side, and that's how you get flood basalts that cover 1 million square kilometres, as they do in India. The melt, of course, I think one thing volcanologists always forget is that the stuff they love that comes out the top is only a tiny fraction of the melt that goes into the system. Probably 9/10 of it, or at least 3/4 of it, gets trapped in sills in the crust, never comes out the surface. So as you become mature, and before you break to an oceanic crust, you then generate the flood basalt, and you intrude stuff underneath. And usually the fractionation happens down here, so that the melt that's coming in is probably 18-20% magnesium, but it fractionates, and as it fractionates, the residual melt gets less dense, because you fractionate out olivine, and there's a density minimum at about 7% magnesium, and that's why everything that comes out the top, including oceanic basalts, are about 7% magnesium content, because you've left the heavier stuff underneath. So that then flows all over the place, and as I said, you get maybe 1 or 2 million cubic kilometres extruded, and maybe 5 times as much, 5 to 10 million cubic kilometres intruded. And that's very typical of a flood basalt province. And we got this idea in the North Atlantic, but it turns out it works for lots of places. One of the key things about it is that you generate the melt really fast, because you're not melting it by heating, you're melting by decompression, so it's instantaneous. And so a hallmark of flood basalts is you get this huge volume in a very short time period. So they're sometimes called large igneous provinces. The sort of name I like better is flood basalt, because it sounds nicer. And they're all over the place. So the place we started off was Iceland, but I'll just show you 3 that are relevant to Africa, which I talked about, I think, at that conference that Ray mentioned. So the Afar is the classic one. As you know, it's rifting along the East African rift system, and that's because it broke above a plume. That's the sort of extent of the thermal anomaly from the plume, and it's formed the Ethiopian flood basalts on this side, the Aden traps on the other, and the East African rift is coming down through here. And of course it's very active still in the rift in the north particularly, so it works very nicely there. Piranha etendica, if you go to Western Africa, there's volcanics there which are same age as the Piranha in South America. This covers 1 million square kilometres, and it was formed just as breakup happened of Gondwana. So this was the situation at breakup time. That's the extent of the thermal anomaly. In this case, most of the melt flowed westward, I think because it was lower topography that side than this side at the time. I mean, as simple as that it was just easier to flow that way. I should say quite a lot of the melt is offshore as well, where it typically exhibits seaward dipping reflectors, but most of it's extruded very close to sea level, and it just gets accumulated up. And of course, when the Atlantic opened, that left a hotspot trail behind it, presently sitting under Tristan da Cunha, which has erupted not so long ago. So this was at breakup time, 120-ish million years ago. Then the third example I just wanted to show is the Karoo, which was older one, formed when Antarctica broke away from Africa. And again, the Karoo, because it's older, it's got eroded much more, so you don't see it like you see the Deccan, where you just can see a huge plateau. But you also get them offshore and in Antarctica in Queen Maud Land. So that was the model. That's why Iceland is there. I just thought I'd show you the African context. But Iceland is there because it's above a mantle plume. The centre of the plume is underneath this ice cap. The white bits are the ice cap. This is the largest ice cap, temperate ice cap. It's more or less at 0 degrees C in the northern hemisphere. And I mean, it's a bit ironic that the hottest place underneath is the coldest place on the surface. It's just because it's hottest underneath, it's pushed it up higher, so you get more ice on top of it. So what I'm going to talk about today is an eruption that occurred from a volcano called Bardarbunga here, and it produced a dike which went nearly 50 kilometers underground before it erupted, and that's what I want to talk about mostly. The rift system in Iceland, the mid-Atlantic ridge comes up here from the Atlantic. It used to go straight through Iceland and out the other side, but the plume, the mantle plume underneath, has been moving eastwards with respect to the plates on top. This is the American plate, this is the European plate. And so as it's moved eastward, as the plume has moved eastward, I said it was right here at the moment, the centre of it, the rift system has found it easier to have a big transform fault in the south and in the north, and you can see it in the earthquakes here. That's the transform fault, back to the original ridge. It was easier to have these two big transform faults and for the rift itself to be over the plume, because the lithosphere is thinner there, it's a bit weaker. So gradually the rift system is moving eastward as the mantle plume moves eastward, and the transform faults on each side are getting longer and longer. Now, presumably, almost certainly, eventually the plume will move so far to the east that the ridge won't like having such huge transform faults, and it will jump back and go back through the middle, I presume. Anyway, at the moment, these yellow ones are the rift systems, and each rift system has a central volcano and then a rift going out each side, and there tend to be dikes propagating out the rift. So the petrology of all the rocks in that rift are pretty well homogeneous. They're all coming from that central volcano, but they'll be different from the one next door. That happens to be Krapla, which is very active. And there's the main rift system here through Bardabunga is quite long. It goes to the south and to the north. So this is the volcano we're going to look at. The Iceland is pulling apart at a half rate of about 10 millimeters a year. And it's oblique, actually, and this will turn out to be important. It's oblique to the direction of the rifts above it, slightly oblique by about 10 or 15 degrees. So here's the bit we're going to look at. This happened in 2014. There's a central volcano there called Bardabunga, which has been active, quite active for a long time, and it just got super active in 2014, and the eruption started in the early part of the year. Well, no, it started in August, although it had been active before that. But I just want to point out too, these ovals are central volcanoes which are all active. There's 1, 2, 3, 4, 5, 6 underneath this ice cap, and that's just because the central rising plume is about 100 kilometers in diameter, and so you get several different streams of melt coming up to the surface. This is the one that's active now. The one to the south, Grimsvötn, has been active very recently in the past, and the biggest historic eruption in the world, which came from Grimsvötn, happened in 1783. It came from this one and flowed all the way down toward the coast here. So that's the tectonic setting, and what happened is this. This is a 2 weeks of earthquake hypercenters, which we recorded in 2014. And instead of coming out the top of the volcano, the melt travelled sideways about 50 kilometers before it erupted in this low point just here. You can see it's a topographic low. And then it erupted for 6 months. And there's 1.8 cubic kilometers of melt erupted. So the melt came out, turned left, came along as a dike, and then erupted. And we happen to have an array there just by providence, really, just by luck, which recorded this incredibly well. It's the best recorded dike in the world. And these earthquakes have been recorded incredibly well. There's 50,000 of them along there. Why didn't it come straight out the top is interesting. We don't know for sure, but this is much higher than here, so the lithostatic pressure is much higher. And it turns out that a few of my students were in this area here, putting some seismometers out, and they were the first people to see the eruption. And the first eruption came out exactly from some craters from a 19th century eruption. So we think there is a path for the melt, which is, as you'll see, at about 6 kilometers depth, which it's reoccupied from the 19th century, late 19th century, and come out exactly the same craters, and then continued to do that. So it's worth just looking. I'll just show you, because that went quite fast. I'll show you that video again. Well, I might do if I can go backwards. Okay, let's do it again. So you can see it came out very quickly, but then, as I say, this is a 2 week period of movie across. And actually, we were really worried it was going to hit this system here. This is the next central volcano called Askja, just there, which we know has got melt underneath it. We've been doing tomography over it. There it is. It's going off the top of the frame now. That was blown out in a massive explosive eruption in 1874, which depopulated the whole of northeast Iceland with the ash. And if this new melt had hit that old stuff, there would have been probably another massive eruption, but it didn't. And the reason it didn't is that this is a topographic low point. The rivers that melt off the ice cap come down this way, and it came out exactly at the lowest point, so there's least pressure above it. And to keep going northwards would have been going into increasing lithostatic pressure. So just for fun, we've got a little utility where you can put the geometry on top of a map anywhere in the world. So here it is. You can look at it yourself. It's great fun. We did an exhibition at the Royal Society not long after this, and we did this utility. 14,000 people came to the exhibition, and they were punching in the postcode or the address of where they lived. And I've put the eruption point exactly under the geology department of Wits, just here. So the lava would have flown, you'll know these places better than me, it flows through Santon to Kempton Park practically. That's the area the lava covered. But the astonishing thing is that it travelled underground from way down here, west of Ennerdale, without erupting. So it's a long, long way, isn't it, to before it actually erupts. And this has been fascinating to look at the tectonics of what was happening on that route. The reason we recorded it so well is that these triangles are all broadband seismometers, and we had 72 of them deployed, mostly to do tomography around Askja, as I said, which is another talk I could show you, but we found melt at 6 kilometres depth there. I was sitting in Cambridge and the students were out downloading, because you can only access this area in the summer, because it's on the Arctic Circle, it's 2,000 metres high, so it's not accessible in the winter. But sitting at home, we had some real-time locations, and I saw this coming northeastwards over a period of a few days. So I thought, it's either going to do something very nasty in Askja, or it's going to erupt in this area. And it just so happened we had a dozen seismometers back in Reykjavik, the capital, which we had deployed on the ice cap for an ice experiment. And so we quickly picked those up, and these were all new deployments here. And they finished deploying literally 2 hours before the eruption started. The one is now it's not under the lava because we removed it, but it's this one right there. We also managed to get 2 right on the ice cap, and we guessed where to put it again, because we put those down on the first day when it was only seismically active back here, so we got them just right. Here we are putting them out on the ice cap, and here we are putting them out in very close to the eventual eruption site, and this was advancing about 1 metre a minute, so this is pulling up the seismometer just before the lava reached it. Now I'm going to spend a bit of time on this diagram because there's a good story here, but it's presented in a way you might not, which is not usual. So on the horizontal axis is the time in days. So this is a 2-week period from the onset to the eruption. The eruption is shown in orange there. And this side is distance from the exit point of the central volcano. Okay, so it's distance vertically against time horizontally. And so these curves, it's distance against time, so it's rate of motion. And it's showing all the hypercenters, well, the epicenters that we mapped. And there's another story to how we did that, because you can't pick 50,000 events manually from 72 seismometers, but we've got a really good automatic system for doing that. And what you can see, if I just pick one of these points here, is that the propagation forward, so this is along the dike, typically it went forward in bursts of 5 to 10 kilometres. So it went forward, paused, went forward, paused, went forward, paused for 82 hours here, went forward, paused a bit, went forward in little bits, went backwards a bit there, went forwards, and so on. So what it's doing is building up pressure. This is right at the tip of the dike. It was propagating forward at rates of about 2 or 3 kilometres an hour. Underground this is the dike at 6 kilometres depth we're talking about. So it will go forward, and then what I think happens is it's run out of pressure, if you like, the driving pressure from the caldera where the magma chamber is, and so it stops while melt feeds through it, rebuilds the pressure, and then it can exceed the fracture strength of the rock and it can propagate forward again, and typically it sort of uses up its pressure after about 10 kilometres, and this one took a long time to replenish and it shot forward. So that's one thing to see. It goes forward in jerks. There's a couple of other things here. You'll see that the seismicity, say when it's reached this point here, it's completely blank, and really is completely blank behind it from 0 to 20 kilometres. And so we're only seeing seismicity in the front 10 kilometres of the dike. So once it's opened a pathway, it's completely aseismic. So there's no doubt the eruption was here at 45 kilometres, but there's almost no seismicity from 35 kilometres back to the source. And that's, as I say, because it's pushed its way forward, you're breaking the rock at the dike tip, but you're opening a channel behind it, which then stays open. And melt, of course, is flowing through here, a lot of melt, but you're just not seeing it because it's an open conduit. And it's a good lesson to tell you that where the earthquakes are might be where the melt is right at the beginning, but it's not where the melt is flowing. In fact, if you look at the moment, if you add up all the seismic moment, and we know the geodetic moment from GPS measurements, it's only about 100th. It's only about 1% of the energy that's released. And we know what the size of the conduit is. It's a tube about 10 metres diameter. And you can do that because we know it's flowing somewhere. It's not flowing in the linear regime because it would freeze inwards and block it up. It's not flowing in the turbulent regime because it would lose too much heat by turbulent flow. It's flowing just on the boundary between laminar and turbulent flow, which is a couple of kilometres an hour, a few kilometres an hour. So there's a lot of richness in this, although there's even more which I'll show you later on when you can refine this. It turns out that some of these places it got stuck are discontinuities where the dike was having to force its way around a corner. And actually one such is here, which we'll see again. And these horizontal stripes, which we thought were artifacts when we first saw it, are actually not artifacts, they're real. There's a discontinuity here that it's difficult for the melt to get through some particular corner, and it's persistently active throughout the eruption thereafter. And you can see a number of them going across. I suppose one last thing to look at is the eruption started with a 4-hour eruption from one particular crater, then it stopped for a couple of days before it went full blast, and then it didn't stop for 6 months. And it's very interesting that when it finally broke its way through to the surface, it did so just here, but the melt had overshot quite a long way by several kilometres, and it was sat at that position for a couple of days before it finally broke through. So it's as if it was trying to find a way through, it was building up pressure, it finally broke through, and it started erupting, but then so much pressure was released by that eruption that the seismicity dropped right back, and you see the V shape before it started building forwards again. And you can see the V shapes when you look at it in several places, particularly after a fast propagation, pressure drops, the seismicity drops at the front, then you build it back up again. So there's quite a lot of information in that. I'm going to concentrate for the next bit on this box here, which is at the northern end, because that's where our coverage is best, but it's also where the seismicity continues. As I said, in the 20 kilometres behind that, there isn't any, because it's just flowing through an open conduit. Now, this is a fault plane solution, which not all of you will follow, but I'll try and explain it. One of the astonishing things about this is a rift system, as I said. We're opening the Mid-Atlantic Ridge here, so you would expect all the earthquakes to be normal faults. You get normal faults on either side of a rift system. Turns out that all the earthquakes are strike-slip earthquakes, which is really weird, at least when we first saw it, though I think there's good reason for it. These are phenomenally well-constrained fault plane solutions, if you've ever worked on them. The actual fault, you can think of this. Well, if you're used to stereograms, it's a stereographic projection of the fault plane, and the fault plane is this particular plane. The other one's an auxiliary plane, and you can ignore that. This is the fault plane, which is sort of northeast, southwest. If you're not used to looking at stereograms, you can think of it as a bird's eye view, and this is the fault plane here. And the trick to constraining it is where the seismic arrivals that are produced, for reasons I won't go into, change from being, with the first pulse being negative polarity to being positive polarity. And the actual waveforms are here, and you can see that that change from negative to positive is defined within a degree or two, and the same again on this side, and it's completely unambiguous about where it occurs. That is phenomenally well constrained for a fault plane solution, but we've got literally thousands like this. So here's that same fault again, or very similar fault. It's probably another one which is very similar. You can see this is the actual fault. It's a left lateral fault. Just think of it as looking on a map from above. So why are we getting left lateral strike-slip faults when it's a rift system opening east-west? Well, here's the reason. The fault direction here is about 038 degrees. The spreading direction is 106 degrees, which is not 90 degrees away. You can see it's less than 90 degrees. So it's pulling obliquely on it, and so it's pulling it obliquely in a left lateral sense. And so these faults are left lateral because of the difference between the direction of the fault and the direction of the extension. And you can see at the surface that the actual dike is propagating at 025 degrees. The fractures that are breaking are at about 038 degrees. And you see those at the surface as well. These have been mapped from surface exposures, sometimes from satellites, sometimes checked on the ground. Very consistent direction. And the reason why you get left lateral here, you can think of this by drawing a little picture of what the stress field is like at the tip of the dike. If you're used to thinking about rift valleys, then just think of this as being vertical, and of course you get inward facing normal faults if this was vertical, and it'd drop inward on the left and inward on the right. If you now rotate that 90 degrees, so we look at a plan view, because the dike is propagating horizontally at 025 degrees, you've got the same stress field still, so you're getting left lateral on the right-hand side if the fault is rotated to the right with respect to the dike, or left or right lateral on the other side. And we'll see examples of both in a minute, right now in fact. And this is published if you want to look at it. So here's the dike propagating from the Caldera and the melt body that it's coming from. It's another story about why it went southeast then turned left, and that's to do with the fact that very recently there was an eruption just a few years ago on the southern side of this. It came out the same path and turned right. There was extension there, so you've used up the extension. In this case it moved left, and of course the extension rate is about 20 millimeters a year. There hasn't been a rifting event here for about 150 years, so that means that there's an extension deficit in the brittle layer of about 3.5–4 meters. And that's what happened here. There was an extension event which allowed the melt to move. The extension event had already occurred on this section of the rift, so it's the next segment that's gone, and I anticipate the next segment to go will be the one to the north. So that's why in the ductile area of the mantle that's a bit deeper, of course, that can just extend, whereas the brittle layer hasn't extended for 150 years, and so the stresses build up at the boundary between the two. And we know that the brittle ductile boundary here is about 6 kilometers depth, so that's why the seismicity is happening at 6 kilometers depth. That's where the highest stress concentration is. Now, what this shows is a map with the dike path, and the kinks I talked about are at various places. The green dots are left lateral strike-slip faults, and I showed you one of these just a minute ago. The red ones are right lateral. The yellow ones are mixed ones. It's quite confused there as it first came out. But let's look at these nice rift segments, a series of dike segments, I should say. They're all right lateral here, and they're pretty well nearly all left lateral up here. Now, the reason is that if we just look at this bottom segment here now of the dike, the actual fabric is rotated to the left with respect to the dike. If you remember, the regional fabric's about 038 here. The dike is propagating at a larger, it's to the clockwise of that. And so, because the dike's propagating at 060 degrees, here's the regional fabric's about 042 degrees here, so we're getting right lateral faulting as the stress field around the tip of the dike is reactivating faults which are there already, faults from the previous occasions. And the Rose diagram of faults is incredibly tight because they're well-constrained fault plane solutions. If we now go to the northern section up here, the regional fabric is, the dike is going rotated left anti-clockwise with respect to the regional fabric. And so here we're activating left lateral fabric, as I said before. And again, it's very tightly, these are the fault plane solutions, incredibly tightly constrained. So that's a very nice story. You can see how it's reactivating the fabric which is there. The next thing we wanted to do was to refine the actual fault plane solution, the actual locations. Those were automatic locations, no human intervention at all. But you can do better than that, and you can see much finer details. There's probably uncertainty of maybe a kilometre on those other hypercenter locations. And the way you do it, you get better locations, is that you take the waveforms and you cross-correlate them and look at the difference. They have very high correlation, and then you line them all up and look at the very small time differences that you need to go from the actual observations to them all being lined up. This gives you subsample relative travel times. So instead of 4 milliseconds sampling, we can go down to probably 1 millisecond. And the reason it works so well is that all those fault plane solutions are pretty well identical. They're all left lateral faults on the same orientation. And so these waveforms and these are all separate, each one of these is a separate event stacked from that northern region, and they're really identical. So we correlate across that window, cross-correlate, we correct, and then you do relative relocation, which I won't talk about, but you can get it much more accurate. And we reckon the relative locations are good to a few tens of meters now. So this was before relocation. This in itself is a better picture than we've got from any other dike in the world. But after relocation, you do that. So look how much it improves it, the relative relocation, after this cross-correlation. And it now means, for instance, that you can see down here, there's a very confused, complicated section of dike, little fingers of seismicity. And this is one of those places where the dike stepped sideways, got stuck before it propagated through. These diamonds, the actual craters out of which the eruption occurred, there were eventually 4 or 5 of them. Although it started off as a fissure eruption, it made a very small graben at the surface before the eruption, as you'd expect, because you've pulled it apart. And there was some melting of the ice cap. This is the ice cap here, where melt came to the surface but didn't erupt. So really a huge improvement, and you can begin to see lots of different features, multiple segments, steps, fractures and dike fingers. So we're now seeing at sort of the outcrop scale. I'm not a geologist because I got fed up with crawling down rabbit holes to see outcrop. You do a lot better around here because you've got good outcrop. But here we're seeing stuff for the first time really with seismicity on the scale of an outcrop of a dike. And you can see features like this in dikes elsewhere. Now, if you look at it in cross-section, the interesting thing here is that I told you all the seismicity was about 6 kilometers below sea level. It's about 7 kilometers below the surface. But it actually spans quite a big depth, at least a kilometer of depth. Now, I told you that the accuracy of these locations is 30 or 40 meters. And I told you that the dike conduit is probably of order 10 meters diameter. Well, maybe it's long and thin, maybe it's 100 meters by a few meters, but it's not going to be 1 kilometer in extent. So what this is telling you is that a lot of this seismicity is not actually just where the dike is, but it's in the surrounding country rock where it's forcing through. And I know sometimes, probably some of you guys have looked at dikes in the field, but you see failure outside the dike quite often in hard rock, going out to several dike widths, I think. And I think that's what we're seeing with the seismicity. We're seeing failure outside of the actual dike where the melt is itself. This is more or less a brittle ductile boundary. It propagates down into the brittle region a bit, But the other striking thing from this cross-section, I don't know if you thought about that, but look, there's no seismicity at all between 6 or 7 kilometres depth and the surface, and yet this is where 1.8 cubic kilometres of rock was extruded, so for sure the melt was flowing up here. So what must be happening is that the fracturing in this area, and of course seismicity is only brittle failure, that it's probably mode 1 failure, that you just open up a crack and then you just expand it by filling it with melt when you make your conduit to the surface. And of course that would not be seismic. You wouldn't see any seismicity from that particularly. So that's another striking thing. Now what I'm going to show you next is a movie which shows this, which actually is quite hypnotic if you can sit and watch this for ages, but you can see the seismicity propagating. This is just in the last 10 kilometres or 15 kilometres of the dike. You can see the dike front propagating forward. Sometimes you can see there's big arcuate propagations going over this kilometre or so depth, sometimes up, sometimes down. But also you can see the dike tip is here, but it's still seismically active way back. There's a good propagation event there. And what that's due to, I think, is the fact that the pressure is fluctuating in this dike, particularly once you get an eruption going. From the surface, you're getting fluctuating pressures. And so the pressure in the dike here is fluctuating a bit, and you're causing failure on pre-existing faults, probably, as those pressures propagate. And there are some areas like back here where it's persistently active, and in the map view you can see that as well. Once the eruption starts, just like I showed you on one of the earlier ones, you actually decrease the pressure in the whole system so much that the seismicity drops by a factor of 10 as well, because there's a free conduit all the way to the surface. This is the time here, it's every second we're showing. So I'll put this on at the end during questions, because I think it's really interesting just to watch it and think about some of the mechanisms of what's going on. And I think, honestly, it's the first time in the world we've seen a dike actually caught it in the act of propagating, and caught it so well in the act of propagating. Because usually we just see the frozen remains. And you'll see as it propagates, it's often on an arcuate vent, and you can't keep your eyes on both at once, but if you could, you'd see what that's doing. Incidentally, I think this and the other video are great for teaching, if any of you teach igneous stuff. And they're all on as supplementary information on the papers that we've published, so you can download this video and use it in lectures if you want. Okay, so I'll leave that running at the end, because we haven't looked at the Caldera end yet, which I want to have time to do. So here's a picture, and this is a one-to-one cross-section. I mean, geologists are famous for not drawing things on one-to-one sections, but we could do here. So this is what we think happens. The dike must open all the way to the surface. This is a plate boundary. We know there was several meters of opening. We see it on GPS at the surface. We see it on INSAR. So the intriguing thing is, why didn't the melt just erupt earlier? Because you've opened a passage to the surface. And I think the reason is that it's quite a thin, narrow dike, particularly initially, and the melt just freezes in it. So the melt must have filled it. You can't leave an open hole, but it froze. And occasionally we got very small subglacial eruptions, and we've done more work on those, but it never really got going until it was in this the lowest point of the profile, where there's least pressure. That's one thing. The other thing is why, and this is the opening phase, the propagation, lots of seismicity. The co-eruption stage dropped by a factor of 10, but still seismically active, and then the post-eruption stage where everything is creaking and groaning and cooling down. So seismicity in the same place, but it decreases by orders of magnitude. The other thing you can see is that there must be a stress concentration at the tip, at the bottom here. And if you do some Coulomb stress modelling, from the opening of the dike, putting in the parameters we know about, here's the opening exaggerated. This is another reason you don't see seismicity in the top section, because as soon as it opens a bit, it militates against further fracture. There's a negative increase in stress, Coulomb stress, and so it's suppressing any faulting that you might want to occur. Whereas in the region where at the tip here, you're actually increasing the Coulomb stress by up to 10 megapascals, which is, that's a lot smaller than the ones you see in mines and so on, but it's quite enough to fracture this. So that's why you see continuing activity near the bottom. The dike itself is probably, the active conduit is probably at the top, I think. We've debated long and hard, is that conduit in the middle of this or is it shallower? Well, it's somewhere around there anyway. Okay, so we've looked at the whole process of the propagation. I just want to look a little bit about what was happening at the other end. This is the driving force at Bardabunga. The caldera is not visible. It's underneath the ice cap. It's a big one, 10 kilometres across. But you can sort of see it here. It's filled with ice, of course, if I put a ring around it. 80 square kilometres of caldera. There's 800 metres of ice here, so there's a fair load on top of it. And what happened during the eruption is that ice surface sank by 65 metres, which is a huge amount. And that's telling you it sank because we've evacuated melt from the storage area underneath it, which is at a depth of about 6 kilometres. So we've extracted melt and it's sunk as you've done so. And that's a very nice, that ties in. What went out at this end what went out from the caldera came out at the eruption site. There's a good balance between them. The seismicity, there's several thousand earthquakes here. There were 85 earthquakes of greater than magnitude 5. And they're mostly on the northern rim. Not so many on the southern rim, but they are on the curved, this is a caldera rim fault. We can do fault plane solutions on that. The locations here are not so good because the seismometers are further away. They're not on the ice cap, so you don't have such good depth control. We have done work with relative relocations, which improves it a bit. But one good thing about fault plane solutions, whether you know what they are or not, is you can get the slip vector out. And the slip vector of each of these little fractures points in the direction of this arrow on the northern side and slightly northwest on the southern side. And that star is actually the center of substance from INSAR measurements and GPS measurements. So actually the fractures are just pointing inwards towards that point. And you can see the seismicity is all above 6 kilometers depth. That's because there's melt at 6 kilometers, so this is the brittle part. The caldera rim fault is inward dipping. There's been a bit of argument about that, but they are inward dipping on each side. But the slip vector is slightly shallower than that, a typical classical angle of 60 degrees or so. And if there was some lovely footage of the Hawaii caldera collapse recently, and you see it collapsing along sort of imbricated rim faults. And I think that's what we're seeing here. And perhaps part of that cloud is because there's a series of slightly imbricated faults collapsing inward as you create space, accommodation space at the bottom. So again, a one-to-one cross-section. This is the whole thing now. So the blue ones are the caldera faults, which are still ongoing. And one of the interesting things is almost as soon as the eruption stopped, these faults carried on, but they reversed polarity. So it's inflating again now. So it'd be really nice if it erupted again. And it's a really nice eruption because it's right in the middle of nowhere, so it doesn't damage anybody. It doesn't hurt anybody at all. But and it's yeah, there's just bare rock there, so you can see what's going on. So that's a caldera. It came from the fault. The melt propagated sideways, then erupted here. There is another feeder outside the caldera. That's another story I could talk about. But it's ponding melt outside here, which is why the melt jumped across there without seismicity. It was already hot, then carried on. And I presume that's because the central volcano is moving eastwards. In the course of time, it will move eastwards. So here's the whole story in those 3 phases of the intrusive phase for 2 weeks, the eruptive phase for 6 months, post-eruptive phase for a year now in this diagram. But this time I've scaled the size of the dots by the magnitude of the events. And so you can see highest magnitude events during the intrusive phase, the propagation phase. They drop considerably once you've opened the vent. And then subsequently they're still in the same place, but they're just much, much smaller. So actually in the post-eruptive stage, you can still see the track of the dike, but it's all just creaking and groaning as it cools down a bit. So I'm going to stop there. I didn't know the noise was working, so that's good. The sound is working. to remind you, I switched off actually, that when you actually see these things, this was about 100 metres, the fire fountain, this was in the early days, just a couple of days after the eruption started, although it's still, so it was a fissure eruption, but it's beginning to build a crater around here. And this brown stuff is sulfur dioxide. It's 35,000 tonnes a day, which is more than the whole of the European Union does. It's really nasty stuff. They stopped people going there just after this, so I was glad we were there when we were. And the energy in this, just to finish off, the energy in this eruption has got the same energy as a Hiroshima-sized bomb every 2 minutes, and it was just carrying on every 2 minutes. So that's my holiday snaps. I just took that on my iPhone. It was just standing there. So as we have questions, I'll just leave that video running. So it's sort of hypnotic, and if you're interested in dikes, it's quite interesting to see how a dike is formed, because when you're a geologist, you just end up seeing the frozen remains of it, and probably a lot of the fabric is the last stage of whatever was going on, and it doesn't really tell you what was happening during the propagation phase. Thank you very much. Yeah.
So that goes to 3-4 kilometers per hour.
No, the 3 or 4 kilometers per hour is just the rapid phases when it went forward. Then it was stopped for a while, then it went forward again.
So compared to the other cases which we know about propagation of the horizontal dike, is it fast, slow, just?
We don't know many others, to be honest. Until Hawaii this last year, we haven't really been able to measure propagations because it's never been recorded as well as this. So I think it's fairly typical, but yeah, but there's not for basalt. I mean, this is pretty low viscosity melt. It's not acidic.
So
it's
nothing extraordinary. So the normal kind of normal rate of propagation.
I think it's fairly normal. Yeah.
What, can you say anything about the sub-Caldera magma chamber?
Yeah.
How big? Shape, cooling rates. Should we expect layering? Is it going to be the bush belt?
Yeah. I could tell you quite a lot about that stuff, and I don't think it's a bushveld or a Skaregard. Almost certainly it's multiple sills with slightly mushy zones between it. We're doing tomography through it, but we've done tomography through Askia, the one to the north, which is very similar. And you can propagate shear waves through it, and yet there's melt there. And that means that the melt is in isolated pods. And there's another talk, we've identified some sills at about 20 kilometers depth. So typically that's where they form. And they're of order of dimensions a kilometer or two, and the thickness is of order 100 meters or so.
So what's the total thickness of the chamber?
Well, it's hard to define because there's lots of layers, and our resolution is such that we can't resolve that finely.
See the actual melt in the chamber by attenuation of seismic waves?
It's what we're hoping to do. We're doing attenuation tomography and also normal velocity tomography there, yeah.
So is there magma there now?
Oh yeah, for sure, yeah. Because it's inflating, and you see that on INSAR. The magma in these things sits around for a long, long time. That was your other question. So Eyjafjallajökull, which erupted in 2010, which again we worked on, though I've not shown it you here, the incoming primitive basaltic melt hit stuff that had been sat there since about 1860 and had been fractionating. It's very fractionated rhyolitic stuff. And when you put the new stuff into the old stuff, that's what triggered the eruption. And probably, that's why I was worried about it hitting Askia. That's been there probably since 1864, 1875 I think it was. So that would be very bad news, yeah.
Thank you for a fantastic talk. I wanted to ask, the cross-section image you showed looking kind of down the dike.
Yeah.
You've got it 50-to-1 ratio almost at surface, and kind of, so it's bubbling along there just underneath the surface.
Oh no, I don't think it is.
You said it's freezing. Could you, and this would be super high-res tomography, could you actually tell spatially and temporally when it's frozen or how it's varying, or is it just the resolution isn't there?
Partly the resolution's not there. These are pretty well 8 to 10 hertz, and the velocity of the rock's 4,000 meters a second, so the wavelength's 400 meters, so or 300 meters ish, really.
You think that's how wide most of the time?
The width was the width at the surface is got from the GPS. So we had GPS. We know it moved 3 meters.
Oh, okay.
Right. So it's a plate boundary. It's spreading. That's how we know that.
Yeah.
It's the old chicken and egg thing, though. So did the rift allow the melt, or did the melt force the rift? Well, it was probably a bit of both. So that's one thing. You can see one thing that melt movement does do. It doesn't make brittle failure, as I said, but it does make sometimes what called very low frequency events. And we have got those when the melt was near the surface, and we've located stuff with that, and we can see it coming up to the surface. The trouble is that the surface conduit acts as a waveguide, and the energy, the very low frequency, goes up the waveguide, and then it propagates out at the surface as the surface waves. So you can locate the event in latitude, longitude, epicenter, but you can't locate the depth. There's some indication we can see it going up, but not very good. So.
Is that almost like the infrasound?
Yeah, well, oh no, it's even lower frequency. It's, yeah, I think it's, the stuff we look at is 0.1. Well, I don't know what infrasound is. I think we're looking at 0.1 to 0.01 hertz, yeah, with that, yeah.
Bob, what's the estimate on the magma pressure?
Well, we don't know the magma pressure, but we do know the pressure at failure. And these faults are failing at pretty low Coulomb stresses. That's differential stress, if you like. Probably a megapascal or two. In some cases, we know it's a few hundred kilopascals, really low. But these are faults that are primed to go. You just give them a little push and they go.
I'm just amazed that there's not that much difference in the relief. You talk
No.
about it erupting in the
Yeah.
valley
Yeah.
compared with what's happening there.
Yeah.
So I mean,
It's 2.2 to 1.6, okay, so there's about 600 meters. Maybe it's a bit more than that, it's 800 meters. Yeah, that's the differential
so
pressure.
that's about 50 megapascals
Yeah.
in low.
Yeah.
It's not a lot.
No, it's not a lot, but faults fail at very low stresses. I think people haven't realized that till recently, at least these faults. What I can show you is, you asked about the melt. This is the melt that's coming just outside the present caldera. The green dots just there. Why I said there was some melt ponded, and that's why the dike jumped that bit. But these, if I go to the next one, I think it is, you can actually do some depth constraints from bits that are carried up. And people in Cambridge have been doing this equilibration between melt, olivine, plagioclase and clinoproxene. And you can do clinoproxene depth control as well. And they all come out at about 6 kilometers depth, which is very consistent. That's from the petrology. This is from the seismics, of course. So I think it's picking up fragments from deeper, because we think it ponds in little sills on the way up. There's good evidence for that. This is probably what it looks like, something like this, underneath the caldera. The series of sills and a mush zone maybe, and the melt predominantly coming from this sort of depth when it propagates sideways. But yeah, we need to do more work on that, and hopefully we will be able to. We're trying to put some seismometers out right over the top, which should give better depth constraint. Very little sign though. The melt probably all comes in here, but it's so hot that it doesn't fail brittly. We've got one earthquake there, which we've looked at hard, and it is real. But nearly all of it is just propagating aseismically. So I keep telling people, you know, it's a beautiful picture, looks like a dike propagating, but it is only a fraction of the energy. It's only the brittle failure around the edge of the dike, actually, is what you see. Why Sigmund is vertical? You mean in the strike slip faulting?
Here, then you were talking about seals. When you about seals, you said that some place in the New York coast
That's because of Caldera.
Sorry, this is the caldera here. Sorry. Yeah. Why is it subsiding vertically? Why is Sigmund? Oh, because it probably hits the density layer, and it's easier for melt to go sideways than vertical. It's probably something to do with the strength of the rock, or So it probably is well stratified horizontally, yeah. Yeah, so why is it a sill and not, why doesn't it keep going as a diet? Yeah. It's partly level of neutral buoyancy, but I don't think that's the whole story. I think there's also strength barriers that it gets stuck against and then it spreads sideways. There's another study I haven't shown you where you can see melt going from one sill to another one, which is just a kilometre away.